Okay, so in these lectures, our aim will be to define differentiability for functions of several variables. So first of all, in fact, there are difficulties in the definition of derivative for functions from Rn to Rm. That difficulty I discussed in my last lecture, but let me recall that if you consider a function from an interval a b into R, then we know that if the limit, and suppose P is a point in AB, if the limit f of P plus H minus f of P upon H when H goes to 0, if this limit exists, we say that function f is differentiable at the point P, and we denote this derivative or this limit by the symbol f dash p. So f dash p is this limit minus f of p upon h. So we know that this is the definition of the derivative. If we want to extend this definition for functions from say Rn to R or Rn to Rm, then this expression will not work, because suppose if you consider f from say some open region of Rn to Rm and define derivative by this formula, then f dash at a point P in U will be limit f of P plus H minus f of P upon H. You can see now this expression in the right side doesn't make any sense, because this H will come from the domain U, where U consists of vectors. So H is a vector, and division by a vector quantity will not make sense. So we have to look for some characterizing properties of the derivative f dash p, and those properties will be taken as the definition. So in order to generalize the idea, first of all we look at this property. What we notice, this I will write down as a theorem, that if f is differentiable, if f from an open interval ab to R, or you can write down this as a characterization, in fact, f from ab to R and p belonging to the interval ab. So f is differentiable at a point P, at P, if and only if there exists a linear map L from R to R such that limit h tends to 0 f of p plus h minus f of p minus LH upon h is equal to 0. This is the property which one can easily observe, and I am stating it as a theorem, and proof is simple to realize that this I will call it as a star formula. If f is differentiable, you can realize that a star formula holds. If f is differentiable at P, so if f is differentiable at P, then by the definition, what will happen? F dash P is equal to limit h tends to 0 f of P plus H minus f of P upon H, and this expression can be rewritten as limit h tends to 0 f of p plus h minus f of p minus h times f dash p or f dash p times h upon h equal to 0. Okay. Now, what do you observe here is that this quantity is a linear function of h, because f dash p is a scalar. We know from this definition that f dash p is in fact tangent of the angle, which this angle theta is the angle which the tangent at the point P makes from x-axis. So, this is a real number. This is a known fact. So, this quantity f dash p into h is a function which is linear in h. In fact, if you look for any function from say Rn to Rm, okay, I will use this. In general, if you consider a function f from Rn to Rm, then this function, if it is linear, it will be written as f of x equal to, let me call it L rather than f. If it is a linear function, it will always be expressed in this manner, where A is a m by n matrix. So, this is how a linear function is characterized. So, if I remove n and m, and L becomes a linear function from R to R, it must be a 1 by 1 matrix. A 1 by 1 matrix means a real number. That is why I am saying with surety that this is a linear function of h. So, this implies formula star holds. So, if f is a differentiable function, formula star holds. Similarly, you can prove the converse part. For the converse part, I will assume that this formula holds for a function f. So, conversely, if star holds for a function f on an interval a b to r, then I will prove that this function is in fact differentiable at some point p. Okay, p is a point in a b. So, conversely, if this holds, what that means? That means there exists a linear map. We are assuming that there is a linear map L from R to R such that f of p plus h minus f of p minus LH upon h in the limiting case, this is 0. This is what I am assuming that this formula holds. Now, since I am assuming that L is a linear map, L must be given by some scalar lambda times h. As we notice that all linear maps from R to R should be written like this, with lambda being a scalar. So, I can rewrite down this as limit h tends to 0, f of p plus h minus f of p minus lambda times h upon h. This limit is 0, and this is same as limit h tends to 0, f of p plus h minus f of p upon h minus lambda equal to 0. Okay? Or this means, this implies limit h tends to 0, f of p plus h minus f of p upon h equal to lambda. So at this point, if you look at it, you will say that this limit exists equal to a well-defined scalar lambda. In other words, this is precisely the derivative of f in our first definition. So this lambda is nothing but derivative of f. Okay, so this means derivative exists. This implies derivative of f exists. So I have proved the theorem from both ways. If f is differentiable, this formula holds. If this formula holds for a linear map, f has to be differentiable at the point P. So this becomes a characterization. So I will call it theorem number 1. So theorem number 1 is a characterization for the differentiability of a real valued function of a real variable. Okay. हम ये सारे characterization इस वजह से देख रहे हैं क्योंकि जो ordinary definition है will not work, and therefore characterizing properties really work as a definition. So this is one such characterization. Now if this one can see that this derivative, this linear map LH equal to f dash p into h. Okay, now this is a linear map and from R to R. So this linear map will be unique. Okay, there is one more important thing, you can call it theorem number 2. The linear map L from R to R given by LH equal to f dash p into h is unique. I am assuming that we are given a function f, then this linear map exists if it is differentiable. Now one can easily show that this is in fact unique. What you do, I will just give you a hint of this theorem also, proof of this theorem. Suppose there are two linear maps which satisfy formula star. So if L1 and L2 are two linear maps satisfying formula star, then I will be having limit h tends to 0 f of p plus h minus f of p minus L1h upon h equal to 0, and limit h tends to 0 f of p plus h minus f of p minus L2h upon h equal to 0. Okay. Now I will subtract 2 from 1. So subtracting 2 from 1 would give me limit h tends to 0 L2h minus L1h upon h equal to 0, because these two terms will cancel out each other. Okay, and if they are, since they are linear map, it will be some lambda 1 into h, and this will be some lambda 2 into h upon h, and limit h tends to 0. If you take h common from both sides, it will cancel out, and what you will be getting from here is that lambda 1 equal to lambda 2. And this implies that L1 equal to L2. That means this linear map is in fact a unique linear map, and once it is unique, I will call it with the name differential of f. Okay, so at this point we can mention this linear map as a differential of f. So this, here comes the definition. The linear map, given a function, this is understood all the time, given a function f from interval a b to r, differentiable at a point p, the linear map whose existence has been ensured by theorem 1, the linear map dfp, I will denote this linear map by dfp from R to R, such that dfp on H equal to f dash p into H is called differential of f at p. Is called differential of f at p. So differential, given a differentiable function, we can think of a linear map which we will be calling as differential of f, and it is defined by this formula. It is same as LH, so I will rather it be denoting by DFP. This is a standard symbol for the differential of f. The same symbol is used in this case of manifold also. So now there is a difference. Differential of f and the derivative of f are two different things. This is a scalar, whereas this is a linear map. When I say differential of f, you think that it's a linear map, and f dash p is the derivative. For function from R to R, it is just a scalar, but when you will consider functions from Rn to Rm, it will be an m by n matrix. So the derivative will be an m by n matrix. That is what we are expecting. Okay. Now, the situation is that when a function is differentiable from interval a b to r, what we have is that delta fp, let me denote. So denote the difference f of p plus h minus f of p by the symbol del f p h. Okay. So del f p h is actually f of p plus h minus f of p. And if you look at this object, it is in fact a change in f when you go from point p to p plus h. I will call it the actual change or a non-linear change. Okay, this is the actual change in f. Or sometimes we also call it a non-linear change in f. And whereas this fellow dfph is in fact f dash p into h. This is also a change in f, and I will rather call it a linear change in f. You will see why it is a change at all. This is a linear change in f. So if I use these symbols, then formula star says that the difference between the non-linear change and the linear change in the limiting case when h goes to 0 is 0. That means function is differentiable if the difference of the two changes goes to 0 faster than h. This is also a terminology we usually use. देखिए जब कभी आप किसी रैशनल फंक्शन की लिमिट ले रहे हों, फॉर एग्जाम्पल यू हैव ए फंक्शन एफ एक्स एंड जी एक्स and suppose x goes to 0 and limit of fx is 0 as well as limit of gx is also 0 when x goes to 0. मान लीजिए मेरे पास एक ऐसा रैशनल फंक्शन है कि जिसका न्यूमरेटर वाला फंक्शन भी 0 की तरफ जाता है और डिनोमिनेटर वाला भी 0 की तरफ जाता है. So what will you say about the quotient of the two? The limit of the quotient will depend on the speed of the limits of the two functions. If this function goes towards 0 faster than gx, then this limit will be 0. Whereas if gx goes towards 0 faster than fx, then this same limit of the quotient will become infinite. For example, if you look at the function x square in x and you take x limit x tends to 0, you will notice that this limit is 0. Whereas if I make it like this, then this time the limit will be infinity. So here what is happening is we are demanding here that this limit goes to 0. In other words, I am demanding that this term should go towards 0 faster than h. Okay. Now this fact is written as, this fact is rephrased as, so I can rephrase it as delta f ph minus df ph equal to OH. Okay. So OH always stands for terms or functions of h which goes towards 0 faster than h. Okay. Or I can rewrite down this as f of p plus h minus f of or I can minus f of p, I can send it over there, so it will become f of p. df ph you have already seen is f dash p into h and plus OH. Okay. So if you are able to express in a small neighborhood of p the function like this, fp plus h equal to f of p plus a linear function of h and plus a term of h which goes towards 0 faster than 0. You will realize little later this is in fact a continuous function of h. So if you are able to express function like this, then the function is differentiable at p. This is a known formula, you already know it. This is a first order Taylor series. And this fellow OH which I just explained is nothing but the remainder term of the Taylor series. Okay. So, okay, I will come to this formula a little later. This is, you can call it double star. First you had formula star and now you have another formula double star. Now, this change between linear change and a non-linear change in f, we need to see in an ordinary functions. You can see it. Look, for example, the graph of the function, if you have a function from an interval ab to r, you can make a graph in R2. Suppose this point is A and this point is B, so the graph is drawn like this, and let me take a point P over here. So this is point P and somewhere over here you have point P plus H. Now let me call this point as A and this point as B, so and this point as C. So this thing is Fp, the height from A to here is Fp, and this much is F of P plus H, and the difference between them is delta Fph. Am I right? Yes. Now when you will consider the limit F of P plus H minus F of P upon H, limit H tends to 0. That means when you will consider the limit of this quotient, what will happen when H tends towards 0? What will happen? B will tend towards A. If you join A and B, this angle will be something phi. So this F of P plus H minus F of P upon H is in fact tan phi. Now in the limiting case, B will tend towards A. So in the next stage, if I take H little smaller, the chord will become this much. Next time it will be further smaller and so on. And when this H goes to 0 in the limiting case, it will be tan of theta, and this chord will become in fact tangent. Okay, suppose this angle is theta, so this will become tan theta. Let me extend it a little further, and you may call it point D. This is C, this is B. So now you see the difference, delta F P H is how much? It is BC. F of P plus H minus F of P, you can see from the figure, it is BC. Now dFPH, it is F dash P into H. F dash P you know is tan theta and into H. Is it right? Yes, sir. Tan theta into H, so I am looking at the triangle DAC. This angle is theta. Tan theta is DC upon H, so H into tan theta will become just DC. Yes, sir. This is DC. And the difference dFPH minus dFPH upon H. Look at this. This is, you have seen it is BC, and this is DC, and BC minus DC is how much? BC minus DC is BD. So what we demand for differentiability, that this difference should go towards 0 faster than H. If you here it is trivial, but if you draw a curve in R3, then you can see that curve is somewhere here and the line is drawn here, so this difference will be larger. Whereas if you draw an exact tangent, then the difference between the distance between the tangent and the curve will be smaller. Okay, then that line will be tangent. I usually tell you in the course of differential geometry that if you have a curve like this and if you draw a line which touches like this, then this cannot be tangent, because the distance between the line and the curve will be too big. Whereas in this case, this distance is smaller than H. So that is why you have a unique tangent like this. Okay, so this is what we demand here. It is like this. All right. Now let me see if there is any other important point which is not covered. All right. Now whatever I have done for functions from R to R, the same thing can be seen, that this thing holds for functions from an interval AB. So as a step forward, consider functions from an open interval AB into something Rm. Okay. Now look at the expression f of p. I am taking p a point in AB, f of p plus h minus f of p upon h. Now still it makes sense. F of p plus h is a vector in Rm, similarly fp is a vector in Rm, the difference of the two is a vector in Rm, and when you divide this vector by h, scalar h, it will remain a vector in Rm. In the limiting case also it will remain a vector. If this limit exists, I will call it f dash p, or the derivative of p, derivative of f at p. Now the only difference is that f dash p, if it exists, it will be a vector in Rm. So the derivative of a function from an open interval into Rm is no more a scalar, it is a vector quantity. You can see what this vector quantity is. What is the graph of the function from interval AB into Rm? Suppose this is the space Rm, and you have a function f from this interval AB into Rm. The graph will be a curve in R3. Okay, and this curve, if suppose P is a point here, so Fp will be the position vector. Is it right? Fp will be a point of the curve. I will join it from the origin, it will become a vector. Okay, so Fp is a vector in Rm, and it's a position vector of a point on the curve. And this vector will be f of p plus h. Okay, and the difference, if you call this point A and this point B, the difference between the two is delta Fp. Is it right? So delta Fp, which you say is a nonlinear change in f, is actually a vector quantity, which we observed otherwise also. Now when you will take the limit of this quotient, P, once again point B will move towards point A, and this vector delta Fp will be a tangent vector. You may call it f dash p. So you can realize that f dash p is a tangent vector at the point P. Okay, it is no more a scalar, it is a vector which is tangential to the curve. Okay, so if I multiply it by scalar h, it will remain a vector in the same direction. It will be little smaller or bigger, I don't know, but it will be a vector along the same. Okay, and the difference between the two is this. This is the difference vector. Okay, so for function f to be differentiable at the point is equivalent to saying that this difference goes towards 0 faster than h. Okay, so everything will make sense. Once this formula 1 holds, the theorem 1 will also hold in this case. So the theorem 1 will be the same. F from AB to Rm is differentiable at P if and only if this limit h tends to 0, f of p plus h minus f of p minus LH upon h equal to 0. So this is the same formula star. Okay, and once again you can show this LH is unique. It was unique in the first case, it is unique in the second case also. Over there proof was easier, so I will call it f dash p into H, or you may also call it df. So this formula also holds. So this is the linear change, this is the non-linear change, and this goes towards 0 faster than H. This is what our demand is for a function f to be differentiable at the point P. Yes. Now the only thing that the difference is that now it's a vector quantity. One can ask what are the components of these vector quantity, these vector, which is f dash p. So the derivative is a vector quantity. So when you have a function from an interval ab to r, ab to rm, okay, now if I take a point p over here, this will go to a vector fp, and it's a vector of Rm, so it will have certain components. These components I will be calling as f1p. Let me write down here. So this is some f1p, f2p, fmp. It will have m component. One can realize here each fi is in fact ui composition f, where ui is a coordinate function on Rm. So these coordinate function, how do these coordinate function work? Coordinate functions ui on Rm to R is a map which maps an m tuple of real numbers to its ith component I. Okay, this is how these coordinate functions work. Okay, so each fi is defined like this. Okay, now f of p is this much. It is f1p, f2p, fmp. So f of p plus h will be same. It will be f1p plus h, f2p plus h. You can see everything is well defined. fmp plus h. If you consider the difference of the two, so f of p plus h minus fp will be equal to slot-wise difference f1p plus h minus f1p. In the second place, you will be having f2p plus h minus f2p, and so on. Last fellow will be fmp plus h minus fmp. This is the m tuple. If I divide this vector by h, in other words, I am multiplying the vector by 1 upon h, the scalar 1 upon h. So each component will be multiplied by 1 upon h. So everywhere we will be having 1 upon h. And if you consider the limit, h goes to 0, so this limit will spread to each of the component. H tends to 0 here, h tends to 0 everywhere, h tends to 0. Now, if these limits exist, they are real valued function of real variable. All fi's are real valued function of real variable. In fact, from an open interval ab to r, if these limits exist, they will be denoted by f1 dash p, and so on. Last will be fm dash p, and this I will be calling as f dash p by definition. So the derivative f dash p will be nothing but it is the m tuple of the derivatives of the components, and this existence is ensured if the existence of each of the derivative of the existence of each component is ensured. So derivative of a vector valued function exists if and only if the derivative of each of its component exists. Okay. So this is important. So if you look at the differential of f over here, so differential of f in this case, what is the case? F is a function from an interval into Rm. So differential of f is again denoted by the same symbol, and definition is also the same. Now this quantity f dash p is no more a scalar, it is a vector, and vector can be considered as a matrix also. So you can consider this is a n by 1 matrix. Okay. So this is a m by 1 matrix whose components I have already written down over here. Okay. Now there are some other important observations, or you can say characterization. If you look at your theorem number 1, I will go back to theorem number 1, which holds for this general case also. So what it says that this difference f of p plus h minus f of p minus this df dash p into h upon h.
F dash p transpose or M? Is it okay, sir? Because F dash p is one row and n columns, and we are writing n plus 1.
No, we whenever you have a linear map from Rn to Rm defined like this, Lx equal to Ax, I consider A to be an m by n matrix, and this is a n by 1 matrix. So the product will be a m by 1 matrix. Okay. So this limit h tends to 0 is 0. This is now our definition for the differentiability. Okay. Now what it says actually, it says that in the limiting case, this difference between delta f ph and the linear change df ph tends towards 0 faster than h. So what we are doing, that this theorem which gives me this formula tells me that there is a linear object to which this nonlinear change is tending towards. Okay. So if there is a linear object in such a way that linear change tends towards is quite fast, it tends towards 0, the difference tends towards 0 faster than h. Is it right? And it's this going of del fp towards dfp must be in a continuous manner. So in fact this suggests another continuous function. So theorem 1 suggests a map, I will call it eta p, defined as follows. I am defining eta ph equal to f of p plus h minus f of p upon h minus f dash p when h is non-zero. Is it visible?
Yes, sir.
Should I write down here? H is not equal to 0 and this term is 0 when h equal to 0. So we are thinking of this map. Now my claim is theorem 3. This theorem tells about eta p. A function f